Okay, let's unpack this. Have you ever looked at a shape, maybe, I don't know, even a simple triangle, and thought, is there some kind of hidden pattern? Like a few basic rules that just make it work the way it does?
Yeah, like finding its blueprint, almost. That's a great way to put it.
Exactly. And, well, that's basically our mission today.
Mm-hmm.
Welcome to our deep dive. We've got a stack of sources here, essentially looking like a geometry guide.
Right.
And it's focused on one specific shape, the isosceles triangle.
A classic. And this source material, it really lays out the definitions, the proofs, the whole logical structure.
It does. So our goal is to kind of cut through all that detail and pull out the really essential knowledge.
The core stuff.
The core stuff, yeah. So you can quickly get what makes an isosceles triangle. Well, isosceles.
Makes sense. Where does the source start us off? The absolute basics.
Okay, so dipping right in, the foundational definition it gives is pretty simple. An isosceles triangle has at least two sides that are equal in length.
At least two. Oh.
Yeah, at least two.
So that raises a question then. What about an equilateral triangle? You know, where all three sides are equal.
Good point. Does that count?
Well, according to our source here, yes, absolutely.
Wow.
An equilateral triangle perfectly fits that at least two sides equal definition. So it says it satisfies all the properties of an isosceles one.
Okay, so it's like a special case of an isosceles triangle.
Exactly. That at least two is the key there. It's inclusive.
Got it. Okay, definition clear. But the source, it doesn't just stop at defining it right. It points to these fundamental rules, these relationships that have to exist because of those equal sides.
Right, and this is where it starts to get really interesting. These aren't just random facts. They're like direct consequences.
Yeah.
Proven outcomes of that initial symmetry.
Consequences. Okay. So what's the first big one? The first main rule the source highlights.
So the first big theorem connects the sides to the angles. It states, if you have two sides of a triangle that are equal, then the angles opposite those sides are also equal.
Opposite. Okay. So equal sides force those specific angles across from them to be equal too.
Precisely. And the source actually walks through the proof. It uses triangle congruence, basically showing you can split the triangle perfectly down the middle into two identical mirror image triangles.
Okay, so that guarantees it. Equal sides mean equal opposite angles.
Yeah.
That's quite powerful. Predictable.
It is. Very predictable.
So what about the other way around? Does it work in reverse?
It does. That's theorem 2. The source calls it the converse.
The converse, right.
It flips it. If two angles in a triangle are equal, then the sides opposite those angles must also be equal.
Ah, okay. So if you measure the angles first, find two the same, bam, you know, the sides across from them match.
Exactly. You know it instantly.
And the source proves this one too, I assume.
It does, yeah. Again, using congruence, just a slightly different approach. AA is congruence specifically, but the underlying idea is the same.
Showing the angles force the sides into equality.
Right. Showing that the equal angles dictate that symmetrical structure, which leads to the equal sides.
Okay, let's zoom out for a second.
Yeah.
We have these two core ideas. Equal sides mean equal opposite angles, and equal angles mean equal opposite sides. Are these basically the main takeaways the source is driving at?
That's spot on. These two theorems, they really are the bedrock. The source does go on, talks about other neat properties.
Like what?
Well, like how the line that bisects the uni angle, the one between the two equal sides, also happens to be the median to the base and the altitude.
Oh, interesting. So it does multiple jobs at once.
Right. But the key point the source makes is that all those other cool behaviors, they all stem directly from these two fundamental rules about sides and opposite angles.
So understanding these two theorems unlocks everything else.
Pretty much, yeah. They're like the genetic code for the isosceles triangle.
That makes a lot of sense. It really does simplify things. If you grasp these two relationships like the source lays them out, then tackling geometry problems with these triangles becomes much, much clearer.
Definitely. You see the why behind its properties, not just the what. It's about seeing that pattern that comes just from having two equal sides.
That symmetry is key.
It really is.
Which kind of leads to a final thought, something for you, the listener, to mull over based on this. Given how this simple, straightforward symmetry, just two equal sides in a triangle, leads to such predictable fundamental rules about its angles and sides, well, what other basic shapes or maybe structures out there might also have surprisingly simple underlying rules?
Yeah, rules that maybe unlock a much deeper understanding of how they work, just waiting to be seen.
Exactly.
Yeah.
Something to think about.